In the current discussion, we have to talk about the curl of a vector in orthogonal curvilinear coordinates. For that, consider a vector v. In this presentation, we have to talk about curl of a vector in orthogonal curvilinear coordinates. For that, consider a vector v. According to Stokes' theorem, v dot dl equal to curl v dot ds. Then curl v equal to integral v dot dl divided by ds. So this is the formula for curl of a vector. Now we have to express curl of the vector v in terms of orthogonal curvilinear coordinates. For that, we have to consider the curvilinear coordinate system. Here q1, q2 and q3 are the three coordinates. In between q2 and q3, q1 is a constant. This is q2 equal to constant surface because we are representing the surface between q1 and q3. This is q3 equal to constant surface because we are considering the surface between q1 and q2. Now consider an element of volume. Consider element of area, not volume. Consider an element of area ds equal to h1 dq1 into h2 dq2 described on a surface q3 equal to constant. Here, consider an element of area ds that is equal to h1 dq1, h2 dq2 described on a surface q3 equal to constant. Say this is q3 equal to constant surface on which we have constructed an element of area ds that is equal to h1 dq1, h2 dq2. See, PQRSP is a closed surface. This is represented by h2 dq2. This line is having the value of h1 dq1. Now we have to find out the value of v dot dl for the entire surface because the component of the surface is along the q3 axis. Therefore, we have to find out the value of curl v along q3. Curl v3 is the component of curl of the given vector V along the Q3 axis. For that, we have to find out integral V dot dl for the closed surface P Q R S P, which is equal to V dot dl PQ plus V dot dl QR plus V dot dl RS plus V dot dl SP. We need the values of vectors along PQ, QR, RS and SP. Let V1 and V2 be the components of V along the Q1 and Q2 axis at point P. See here, at point P, V1 be the component of the vector V along Q1 and V2 be the component of the vector V along Q2. The rate of change of V1 with respect to Q2 is dou V1 by dou Q2. The rate of change of V2 with respect to Q1 is dou V2 by dou Q1. Now we have to find out the component of the vector along the path PQ, QR, RS and SP. The component of the vector V along PQ equal to V1. The component of the vector V along the path QR equal to V2 plus dou V2 by dou Q1 into PQ1. See here, along this path, this path is parallel to Q2. Therefore, Q2, the value of the vector is V2. Because the component of the vector along the path Q2 is V2, and the variation of V2 with respect to Q1 is dou V2 by dou Q1 into dQ1. Then consider the path RS and SP. The RS is opposite to the direction of Q1. Therefore, we have to take the component of the vector along the path SR. The component of the vector V along the path SR is V1 plus dou V1 by dou Q2 into dQ2. See here, this path SR is parallel to Q1. Therefore, the component of the given vector V is V1, but the variation is possible with respect to Q2. So, V1 plus dou V1 by dou Q2 into dQ2 is the component of the vector V along the path SR. And consider this path PS. This PS path is parallel to the coordinate Q2. Therefore, the component of the vector V along PS is only V2. Because we pointed out earlier, at the point P, the component of the vector along Q1 is V1. At the point P, the component of the vector V along Q2 is V2. Therefore, simply we have to write V2. The component of V along the path PS equal to V2. See this variation. The component of the vector V along PQ is V1 alone. Component of V along the path PS is V2 alone, because at the point P, the component of the vector parallel to Q1 is V1. At the point P, the component of the vector parallel to Q2 is V2. So that we are considering the paths PQ and PS. But the component of the vector along QR and SR are having the rate of change of V1 and V2 with respect to the two coordinates Q1 and Q2, because these 2 points are not at P, they are far away from P. Therefore, the rate of change is also added to the components of the vectors V1 and V2. Now we have to find out the integrals one by one. Integral V dot dl PQ or SP. Check it out. Integral PQ or SP equal to integral V dot dl PQ plus integral V dot dl QR plus integral V dot dl SP, that is RS. RS plus integral V dot dl SP. Now consider the first integral V dot dl into PQ. The component of vector V along PQ is V1. So the vector value is V1 and the line segment along this path is h1 into dq1. This is the value of dl. h1 dq1. Now consider the second integral v dot dl qr. Along the qr, this is the value of v vector component v2 plus dou v2 by dou q1 into dq1. The value of dl along qr. The value of dl along qr is h2 dq2 because this qr is parallel to this ps. Therefore, h2 dq2. h2 dq2. Now come to this third integral v dot dl along rs. But we are taking the value of vector component along the path SR, not RS. Therefore, we have to keep a negative sign here. Minus of this quantity V1 plus dou V1 by dou Q2 into dQ2. Entire is multiplied by the line segment DL. Along SR, the line segment is H1 dQ1 because this is parallel to SR is parallel to PQ. So here we have to put H1 dQ1. Final path is integral SP, but we have taken PS. Therefore, we have to introduce a negative sign minus V2 and consider the path P1. PS is having the line segment of H2 dQ2. H2 dQ2. Now simplify this. This is equal to V1 H1 dQ1 minus of V1 into H1 dQ1 cancelled out. V2 dQ1 H2 dQ2 minus of V2 H2 dQ2 cancelled out. So dou V2 by dou Q1 into dQ1 dQ2 H2 minus of dou by dou Q2 B1 H1 into dQ1 dQ2. This is the remaining term. This is equal to dou by dou Q1 now V2 H2 dQ1 dQ2 minus dou by dou Q2 of V1 H1 into dQ1 dQ2. This is the value of V dot dl PQRSP. Now you have to do the same. Integral V dot dl PQRSP, which is equal to double dou Q1 of V2 H2 dou by dou Q1 of V2 H2 dq1 dq2 minus dou by dou q2 of v1 h1 minus dou by dou q2 of v1 h1 into dq1 dq2. Verify once again. Dou by dou q2 of v1 h1 dq1 dq2. Okay. Now this is dou by dou q1 of v2 h2 minus dou by dou q2 of v1 h1 entire is multiplied by dq1 dq2. The curl of the vector along q3 equal to v dot dl divided by ds. This is equal to integral v dot dl divided by h1 into h2 dq1 dq2, because this is the value of ds. Now the above equation becomes del cross v3. This is the component of curl v along the coordinate q3 equal to 1 by h1 h2 dq1 dk2 into dou by dou q1 v2 h2 minus dou by dou q2 into v1 h1 entire is multiplied by dq1 dq2. This is further modified as 1 by h1 h2 dou by dou q1 of v2 h2 minus dou by dou q2 of v1 h1 del cross v3. This is the component of del cross v along q3. In the same manner, we may find out del cross v, the component of curl v along 1, that is equal to 1 divided by h2 h3 dou by dou q2 of v3 h3 minus dou by dou q3 of v2 h2. Then curl v of 2, the component of curl v along q1. This is del cross v along q1. This is del cross v along q2. 1 by h1 h3 dou by dou q3 v1 h1 minus dou by dou q1 of v3 h3. This is del cross v along q2. Now by adding these three, that is curl v along q1 plus curl v along q2 and curl V along Q3 vectorially, you can get curl V equal to 1 divided by H1, H2, H3, E1 cap, H1, E2 cap, H2, E3 cap, H3, dou by dou Q1, dou by dou Q2, dou by dou Q3, V1 H1, V2 H2, V3 H3. This is the value of curl of a vector in orthogonal curvilinear coordinates.